Hello there, and welcome to my introduction to machine learning. In the following 10 minutes, I will try to explain the core concepts of machine learning to you, and I will do so or try to do so by starting with a pretty easy example and then by transferring the insights you will probably or hopefully have to a more complex problem. So let's start. So as I said before, the starting example is pretty easy. What you can see here is the relationship between different sand granule diameters and the related slope on a particular beach. And for small sand particles, the beach is not that steep. And as the sand particles get bigger, the beach is getting steeper. So here on the side, you can find another visual support of this relationship. Small sand particles will lead to a beach that is not that steep. Bigger sand particles will lead to a beach that is much steeper. So if you try to come up with a relationship between the different diameters and the different slopes, the easiest one you might imagine is a linear one. Actually, this is already a core concept of machine learning to search for a correlation between an input, in this case the different diameters, and an output, in this case the different slopes. So let's pretend that the actual relationship is a line or a linear one. So how do we know if this line, with its equation here, is a good one? You might have already heard of the sum of squared errors. And the sum of squared errors here is a so-called cost function. And machine learning is nothing more than to optimize your model parameters, in our case your line slope and your intercept, to minimize a certain cost function. Here in our case, the sum of squared errors. And the sum of squared errors is calculated as follows. You just take the vertical distance between a slope you've calculated for a particular diameter with your model and the actual slope you've measured in your sample data for a particular diameter. And then you're going to square this difference here, or the vertical distance. And you're going to do the same for all the other vertical distances here. You're going to square them and add them up. And what you get then is your sum of squared errors. So the blue line you can see here is the optimal linear equation if you take the sum of squared errors as your measurement of quality. This means for these parameters or these values here of your parameters, this is actually the smallest sum of squared errors you can actually get. But how do we get here? How do we find our optimal parameters if we don't already know them? So let's assume we don't know the optimal line slope right now, but the optimal intercept is already given. So how to optimize this value of our line slope to minimize the sum of squared errors? What you can see here is the actual value of our sum of squared errors for different line slopes. And our line slope right now is at 22.31, and the resulting sum of squared errors is about 45.66. This gray line here, the sum of squared errors for different line slopes, is just a helper for you. And normally we don't have something like this in machine learning problems. So assume you are here. You're standing here with this line slope of 22.31. How do you know how to change the value of your line slope if you don't know this exact gray line? How do you know if you should increase or decrease the value? Right, all you have to do is to calculate the derivative of our cost function. And the reason why we are doing this is that it's computationally less demanding than to calculate this gray graph here, especially for thousands of parameters. So this derivative or gradient has the nice property that it points into the direction of maximum increase of our cost function. So all we have to do now to decrease our sum of squared errors is to multiply our derivative of 13.75 by -1, and to make sure that we won't miss our minimum here, we also multiply this derivative by a certain step size, in this case by 0.1. And what we are doing after is to just repeat this step several times. And by this way, we are slowly reaching our minimum, and our line slope will near its optimal value. So this process you can see here is called gradient descent. You might have heard of it before. Actually, there's another important algorithm hidden in this process called backpropagation. Backpropagation is used to calculate the derivative, and it's especially useful if you want to calculate a derivative for a function with thousands of parameters. To keep this video short, we won't talk more about backpropagation. So you might ask yourself, okay, I was promised machine learning, but all you told me was about line equations. The funny thing is that a line equation could be interpreted as a neural network. To be honest, a pretty simple one. As you can see here, we've got our input x, our sand particle diameter. This input is multiplied by our line slope a. Then we add an intercept b. And in neural networks, there's often a so-called activation function. Here in our case, we don't want to change the value we've got here, so all we do is to multiply it by 1, and we will get our output, the beach slope y. So this is what the representation in Keras, a pretty popular machine learning framework, looks like. We've got our input, then our cell. The activation is linear here, we don't want to change the value we've got here. And what we are going to do now is to initialize this neural network with the same values we did before with our already optimal intercept, but with a non-optimal line slope. We are going to use the cost function, the mean squared error. This is the sum of squared errors divided by the number of samples. So we will divide the sum of squared errors by 11 to get our mean squared error. Then we optimize it by gradient descent. The learning rate or step size is 0.1, like you've seen before. And then we're going to repeat this optimization step for 1,000 times. So let's do this. And what you can see here is the learning process. And let's just go fast forward. And the actual result for the line slope we've got after 1,000 optimization steps is 17.163 something, and the intercept didn't really change because it was already optimal here. So I hope you get now that what you've seen before was an actual machine learning example. We did conceptually nothing different here. So why do we need complex models like neural networks or other more sophisticated models? And there are, of course, nonlinear correlations for which line equations aren't sufficient. Take, for example, the MNIST database, consisting of thousands of images, 28 by 28 pixels, and their related label. And the aim here is to find a model that is capable of taking these pictures, 28 by 28 pixels, and to come up with a related label or number that is actually shown in the image. So for example, if you give in this picture here, your model should give an output of 0 or 1 here, 2 here, 3 here, and so on. So what to do to get the relationship between our pictures and the corresponding labels? All we have to do is, with our neural network, is to increase the input layer. So from 1 neuron, you've seen before, to 784. This is 28 squared because of the resolution of our images. Instead of one linear cell, we're going to take 15 cells. So we've got our B1, B2, B3, B4, and so on, and the edges correspond to our weights of A1, A2, A3, A1000 something. And instead of one output, we've got 10 outputs or 10 output nodes. Every node is corresponding to a certain number. So how does an actual training step look like? For example, we take the image of a 2, so it's one of our training images, and it consists of 28 by 28 pixels, and every pixel has a value of 0 or something in between 0 and 1. So 0 corresponds to a white pixel, and 1 corresponds to a black pixel, and if it is gray, it's something in between 0 and 1. And we feed these pixels into our neural network, so we have to increase our input layer from just one node to 784 equals 28 squared, and multiplying these values by our weights here, so A1 to A1000 something, adding up a bias or an intercept, and as I said before, we use a linear activation after, so what we're going to do here is to multiplying our results here by just 1. And then there's another transformation step so that we can interpret our output values as probabilities. So 0.07 means that the probability that our input image is showing a 0 lies around 7%. So as you can see, our model isn't that good because the probabilities our model gives us here seem quite random. So how do we improve our model? Conceptually, the steps are exactly the same to these you have seen before for our easier example. So we have to calculate our squared errors. We're going to take the output values of our model, and we're subtracting a 0 if our training image doesn't show the corresponding number, and a 1 if our input image shows the corresponding number, so 2 here. And then we're going to add up all these squared errors, and next we have to repeat this step for all our other training images and add the sums up, so we've got our real sum of squared errors. So all we have to do now is to calculate our derivative of our sum of squared errors, our cost function, or our mean squared error, however you want to call it, as a function of our parameters, our a's here and our b's here. And afterwards, we've got our gradient. This time it's a multidimensional vector, not a scalar value any longer, by -1, and by a certain step size or learning ratio. And then you have to change the parameters accordingly to the values you get, and repeat this step several times, and hopefully your model will improve. So as we did before, we're going to actually calculate our example. So this time we've got 784 input nodes, our pixels, and our hidden layer consists of 15 cells. the activation is linear, so we're going to multiply our resulting values by just 1. And then we've got 10 output nodes. And the activation function we want to use after is softmax, so our resulting values could be interpreted as probabilities. Our loss function or cost function is the mean squared error. We're going to use gradient descent with a learning ratio of 0.1 for improving our parameters, and we want to output the accuracy. So so how well our model will perform on training data and testing data. Testing data means we're going to exclude some of our data set from training, so our model won't see this data during training. And so we could see if our model will also perform or generalize on new data. And we will repeat this learning or training step 20 times, and let's see what happens. So our model is training with 60,000 training images, and repeat this step for 20 times. And what you can see here is the accuracy on our training data. So right now the mean squared error is improving or decreasing, and the accuracy will increase. So let's wait until our training process finished. Just another second. Okay, so our final error on our testing data is something like this. It's not easy to interpret this value, so what does it mean? But the accuracy is around 93%. So our model is able to get 93% of our training data or training images it has never seen before right. So it's quite good for an easy model like this. You've got some possibilities to improve this model. So the world record is something around 99.6% in actual recognition accuracy. Yeah, but so far I hope you enjoyed this short introduction into machine learning. Leave me your comments on my blog, lausbird.com, and maybe you found some inaccuracies or errors in my presentation. Just leave them there and I will try to improve this presentation. Have a nice day. Bye bye.